IEEE standards offer guidance for performing arc flash hazard calculations. Specifically, IEEE Standard 1584-2018 provides a guide, and IEEE Standard 1584.1-2016 offers an amendment focusing on direct current systems. Several technical papers and articles address this topic. A paper titled Arc Flash Calculations for DC Systems by David B. Altman and John D. McDonald, published in 2017, is a valuable resource. Another paper, Arc Flash Hazard Analysis for DC Systems by G. Murhan and P. Arankumar from 2019, offers further insights. Additionally, the paper Arc Flash Analysis for DC Systems by P. M. Cheng T. J. Tang and A. B. Duncan, published in 2007, provides a detailed analysis. Software tools are available to assist with DC arc flash calculations. Easy Power offers an arc flash analysis tool capable of handling DC systems. SKM Powered Tools includes modules specifically designed for DC arc flash calculations. ETAP provides analysis capabilities for DC systems, encompassing arc flash hazards. Several other resources are beneficial. NFPA 70E, the standard for electrical safety in the workplace, is crucial for understanding safety practices. IEC 61641 addresses protection against electrical shock, covering common aspects for installation and equipment. The IEEE IAS Task Force on DC arc flash provides a platform for information and resources related to DC arc flash hazards. Key considerations for DC arc flash calculations include: firstly, DC systems exhibit different arc characteristics, necessitating specific calculations. Secondly, the fault clearing time for DC systems is typically slower compared to alternating current systems, resulting in longer arc durations. Thirdly, the arc energy for DC systems is generally higher than that of alternating current systems. Fourthly, the type of protection device employed can significantly impact the arc flash hazard analysis. Understanding these standards, papers, tools, and considerations is essential for accurately assessing and mitigating arc flash hazards in DC systems. Further details on these resources can be found through online searches and professional electrical engineering associations. Accurate arc flash calculations are vital for ensuring worker safety and preventing electrical accidents. When performing arc flash calculations for DC systems, several factors must be taken into account. These factors are crucial for accurately assessing the potential hazards and implementing appropriate safety measures. Firstly, voltage level is a primary determinant of the arc flash hazard. Higher voltage levels generally lead to more severe arc flash incident. Secondly, available fault current is another critical parameter. The magnitude of the fault current directly influences the arc energy released during an arc flash. Thirdly, system grounding configuration plays a significant role. Different grounding methods can affect the fault current path and the overall arc flash hazard. Fourthly, electrode configuration is important. The arrangement and spacing of conductors can impact the arc formation and its characteristics. Fifthly, enclosure size and geometry influence the arc flash. Confined spaces can lead to higher arc flash energies due to reflections and increased pressure. Sixthly, clearing time of overcurrent protective devices is a key factor. Faster clearing times reduce the duration of the arc flash and minimize the energy released. Seventhly, the type of overcurrent protective device used is important. Fuses, circuit breakers, and other devices have different characteristics that affect their response to fault currents. Eighthly, the presence of DC capacitors in a system can impact the arc flash. Capacitors can store energy and contribute to the arc flash hazard. Ninthly, the battery impedance influences the fault current. Lower impedance batteries can deliver higher fault currents, increasing the arc flash hazard. Tenthly, the cable impedance affects the fault current. Longer cable runs and smaller conductor sizes can limit the fault current. 11thly, arc resistance can vary depending on the materials and conditions. Arc resistance influences the arc voltage and current. 12thly, ambient temperature can affect the arc flash. Higher temperatures can increase the arc plasma temperature and energy. 13thly, altitude can also play a role. Higher altitudes have lower air density, which can affect the arc characteristics. 14thly, the presence of nearby grounded surfaces can influence the arc flash. Grounded surfaces can provide a path for the arc current and affect the arc energy. 15thly, the type of equipment involved is important. Different types of equipment have different insulation levels and protection features. 16thly, the maintenance practices in place can impact the arc flash. Regular maintenance can help prevent equipment failures and reduce the likelihood of arc flash incidents. 17thly, the training of personnel is crucial. Properly trained personnel are more likely to recognize and avoid arc flash hazards. 18thly, the use of personal protective equipment, or PPE, is essential. PPE can protect workers from the thermal and blast effects of an arc flash. 19thly, the implementation of arc flash hazard reduction methods is important. These methods can include current limiting devices, high resistance grounding, and arc flash relays. 20thly, the regular review and updating of arc flash studies are necessary. Arc flash studies should be updated to reflect changes in the system and to incorporate new data. These factors should be carefully considered when performing arc flash calculations for DC systems. By accurately assessing these factors, engineers can implement effective safety measures to protect workers from the hazards of arc flash. For example, consider a 750 volts DC traction power system used in a railway application. The available fault current at a specific point in the system is calculated to be 10,000 amps. The system is grounded using a solid grounding method. The electrode configuration consists of two parallel conductors spaced 6 inches apart. The enclosure is a metal cabinet with dimensions of 2 feet by 2 feet by 4 feet. The clearing time of the overcurrent protective device is 0.1 seconds. The overcurrent protective device is a DC circuit breaker. The system includes a bank of capacitors with a total capacitance of 1000 microfarads. The battery impedance is 0.1 ohms. The cable impedance is 0.1 ohms per foot. The arc resistance is estimated to be 0.1 ohms. The ambient temperature is 25 degrees Celsius. The altitude is sea level. There are nearby grounded surfaces within 1 foot of the conductors. The equipment involved is a DC switchgear. The maintenance practices include regular inspections and testing. The personnel are trained in arc flash safety. The PPE used includes arc-rated suits, gloves, and face shields. Arc flash hazard reduction methods include the use of current limiting fuses. The arc flash study is updated annually. Using this information, an arc flash study can be performed to determine the incident energy and arc flash boundary. The results of the study can be used to select appropriate PPE and implement other safety measures. The incident energy is the amount of energy that a worker would be exposed to during an arc flash event. The arc flash boundary is the distance from the arc source at which the incident energy is equal to 1.2 calories per square centimeter, which is the threshold for second-degree burn. By understanding these parameters, engineers and safety professionals can effectively mitigate the risks associated with DC arc flash hazards. The calculation methods for DC arc flash differ significantly from those used for AC arc flash. The primary reason for this difference lies in the nature of the current flow in each type of system. In AC systems, the current alternates direction periodically, typically 50 or 60 times per second. This alternating current creates a sinusoidal waveform that crosses zero twice in each cycle. When an arc occurs in an AC system, the current tends to extinguish itself each time the waveform crosses zero. This self-extinguishing behavior reduces the duration of the arc and the amount of energy released. In contrast, DC systems have a constant current flow in one direction. There are no zero crossings to interrupt the arc. Once an arc is initiated in a DC system, it tends to be sustained until the circuit is interrupted by an overcurrent protective device. This sustained arc results in a longer arc duration and a higher arc energy compared to AC systems. Another difference between AC and DC arc flash calculations is the arc voltage. In AC systems, the arc voltage is typically a function of the arc current and the system voltage. In DC systems, the arc voltage is more complex and depends on factors such as the electrode material, the gap distance, and the arc current. The arc resistance also differs between AC and DC systems. In AC systems, the arc resistance is typically lower than in DC systems. This lower resistance contributes to higher arc currents and higher arc energies in AC systems. Due to these differences, the calculation methods for DC arc flash must take into account the unique characteristics of DC arcs. Several models have been developed to estimate the arc voltage, arc current, and arc energy in DC systems. One common model is the Pockert model, which is based on experimental data and takes into account the electrode material, the gap distance, and the arc current. Another model is the Stokes and Oppenlander model, which is based on theoretical considerations and takes into account the plasma properties of the arc. The IEEE 1584.1 standard provides guidance on performing arc flash calculations for DC systems. The standard recommends using a combination of empirical data and theoretical models to estimate the arc flash hazard. The standard also provides equations for calculating the incident energy and arc flash boundary. The incident energy is calculated based on the arc voltage, arc current, arc duration, and the distance from the arc. The arc flash boundary is calculated based on the incident energy and the threshold for a second-degree burn. It is important to note that arc flash calculations for DC systems are complex and require specialized knowledge and software. Engineers should consult with experienced professionals and use validated software tools to ensure accurate results. In summary, the calculation methods for DC arc flash differ significantly from those used for AC arc flash due to the unique characteristics of DC arcs. The IEEE 1584.1 standard provides guidance on performing arc flash calculations for DC systems. Engineers should consult with experienced professionals and use validated software tools to ensure accurate results. Several software tools are available to assist with DC arc flash calculations. These tools can automate the calculations and provide detailed reports on the arc flash hazard. EasyPower is a popular software tool that includes an arc flash analysis module for DC systems. The EasyPower module can calculate the incident energy, arc flash boundary, and PPE requirements. SKM Power Tools is another software tool that includes modules for DC arc flash calculations. The SKM modules can model various DC system configurations and calculate the arc flash hazard. ETAP is a comprehensive software tool that provides analysis capabilities for DC systems, including arc flash hazards. The ETAP software can simulate various DC system operating conditions and calculate the arc flash hazard. These software tools typically use a combination of empirical data and theoretical models to estimate the arc voltage, arc current, and arc energy in DC systems. The software tools also incorporate the equations and methods recommended in the IEEE 1584.1 standard. When using these software tools, it is important to input accurate system data, including voltage levels, fault currents, grounding configurations, and electrode configurations. The software tools can then generate detailed reports on the arc flash hazard, including incident energy levels, arc flash boundaries, and PPE requirements. These reports can be used to select appropriate PPE and implement other safety measures. It is important to note that software tools are only as good as the data that is input. Engineers should carefully verify the accuracy of the system data before using the software tools. Engineers should also consult with experienced professionals to interpret the results of the software tools and to ensure that the arc flash hazard is properly assessed. In addition to software tools, several other resources are available to assist with DC arc flash calculations. The NFPA 70E standard provides guidance on electrical safety in the workplace. The standard includes requirements for arc flash hazard assessments, PPE, and training. The IEC 61641 standard addresses protection against electrical shock. The standard includes requirements for grounding, insulation, and other safety measures. The IEEE IAS Task Force on DC arc flash provides a forum for sharing information and resources on DC arc flash hazards. The task force publishes technical papers, articles, and other resources on DC arc flash. These resources can be helpful for engineers and safety professionals who are responsible for assessing and mitigating arc flash hazards in DC systems. By using these resources, engineers can ensure that they are following best practices for electrical safety and that they are protecting workers from the hazards of arc flash. The selection of appropriate personal protective equipment, known as PPE, is a crucial step in mitigating the risks associated with DC arc flash hazards. PPE is designed to protect workers from the thermal and blast effects of an arc flash. The type of PPE required depends on the incident energy level at the work location. The incident energy level is determined by performing an arc flash study. The NFPA 70E standard provides guidance on selecting appropriate PPE based on the incident energy level. The standard categorizes PPE into different hazard risk categories, or HRCs. Each HRC corresponds to a specific range of incident energy levels. For example, HRC 1 corresponds to incident energy levels between 1.2 and 4 calories per square centimeter. HRC 2 corresponds to incident energy levels between 4 and 8 calories per square centimeter. HRC 3 corresponds to incident energy levels between 8 and 25 calories per square centimeter. HRC 4 corresponds to incident energy levels above 25 calories per square centimeter. For each HRC, the NFPA 70E standard specifies the minimum PPE requirements. These requirements typically include arc-rated clothing, gloves, face shields, and footwear. Arc-rated clothing is designed to protect the body from the thermal effects of an arc flash. The clothing is typically made of flame-resistant materials that will not melt or ignite during an arc flash. Arc-rated gloves are designed to protect the hands from the thermal effects of an arc flash. The gloves are typically made of leather or other insulating materials. Face shields are designed to protect the face and eyes from the thermal and blast effects of an arc flash. The face shields are typically made of polycarbonate or other impact-resistant materials. Arc-rated footwear is designed to protect the feet from the thermal effects of an arc flash. The footwear is typically made of leather or other insulating materials. In addition to the minimum PPE requirements specified in the NFPA 70E standard, employers may choose to provide additional PPE to enhance worker safety. For example, employers may provide arc-rated suits which offer full body protection from the thermal effects of an arc flash. Employers may also provide arc-rated hoods which offer additional protection for the head and neck. It is important to ensure that workers are properly trained on how to use and maintain PPE. Workers should be trained on how to inspect PPE for damage, how to properly don and off PPE, and how to clean and store PPE. Workers should also be trained on the limitations of PPE and the importance of following safe work practices. By selecting and using appropriate PPE, employers can significantly reduce the risk of injury or death from arc flash hazards. Regular arc flash hazard training is crucial for ensuring the safety of electrical workers. This training should cover a range of topics, including firstly, the nature of arc flash hazards, explaining what causes them and the potential consequences. Secondly, arc flash hazard assessments, teaching how to identify potential arc flash hazards in the workplace. Thirdly, safe work practices, outlining procedures for working safely around electrical equipment. Fourthly, the selection and use of PPE, ensuring workers know how to choose and use appropriate protective gear. Fifthly, emergency procedures, preparing workers for responding to arc flash incidents. Sixthly, the relevant standards and regulations such as NFPA 70E and OSHA guidelines. Seventhly, the importance of de-energizing equipment before working on it whenever possible. Eighthly, the use of lockout-tagout procedures to prevent accidental energization. Ninthly, the proper use of test equipment to verify that equipment is de-energized. Tenthly, the importance of maintaining a safe working distance from energized equipment. 11thly, the use of barriers and other protective measures to prevent contact with energized equipment. 12thly, the importance of reporting any electrical hazards or incidents. 13thly, the continuous review and improvement of safety procedures. The training should be tailored to the specific hazards and work practices of the workplace. It should also be provided on a regular basis to ensure that workers stay up to date on the latest safety information. In addition to formal training, employers should also provide ongoing safety reminders and toolbox talks. These brief safety discussions can help reinforce key safety concepts and promote a culture of safety. It is also important to involve workers in the development and implementation of safety procedures. Workers can provide valuable insights into the hazards they face and can help identify ways to improve safety. By providing regular arc flash hazard training and promoting a culture of safety, employers can significantly reduce the risk of arc flash incidents.